concepts will help you solve the activity questions, right? So DFS will certainly do recursion, and the adjacency matrix, I'll do that as a part of DFS. Any other doubts that you have from graphs?
No, sir.
Okay. All right. So let's do the following. I just share my screen now. Different set of slides. Can you please confirm if my screen is visible?
Yes, sir. Yes, sir.
It's visible, sir.
Okay. So just again, once again, apologies for starting so late. It's like half an hour late, and it was not intentional, like somehow kind of mistake.
No issues.
Yeah. So
Sir.
my name is Karthik. So I was a part of the CT course in 2020 when it was first designed. And then subsequently, I was an instructor for Python, and then now I'm an instructor for the machine learning courses in the diploma level, right? So that's a very brief background of where I come from. So let's start with. Sorry. Yeah. So let's start off with recursion, right? So I'll take the same examples that Professor Madhavan has considered, and we'll look at a visual way to understand recursion, at least to the extent possible. Okay, we'll take factorial. Okay, so I hope you're all aware of factorial, right? So n factorial is n into n minus 1, so on till 1, right? So that's what we need to compute. And you have a code like this, right? So can someone tell me what makes this code recursive? What gives this code this term? Why am I associating this word recursion with this code?
Repeatedly calling the same function.
Correct, right? So you repeatedly call the same function, but does that, so from where do you call the same function or procedure in our case?
Procedure itself.
Correct, right? So you repeatedly call the procedure, in this case factorial, from the procedure itself, right? So you have a procedure factorial, and somewhere inside that piece of code, so procedure and function, let's use them interchangeably. So somewhere inside that function, you call that procedure again, right? So factorial of n, somewhere factorial of something else is being called. So this kind of self-referencing, right? I am calling myself. This kind of operation is called recursion. Okay, so this is a recursive piece of code. So I'll just go ahead and execute this for some values, right? So for a particular value, let's say factorial of 3. Okay, I want to evaluate factorial of 3. So let's try to understand what is really happening. Okay, so when I call factorial of 3, you all know normal procedures, how they work. So is this condition, if condition satisfied, is n double equal to 0?
No, sir.
No, sir.
This, I won't enter this if block. So what happens? So I go to the else block and I see that I need to return something, right? So I'm going to return 3 into factorial of 2, right? N into factorial of n minus 1 is, in this case, n is 3. So I'll write the procedure call here on the left hand side, and corresponding to it, whatever the function returns, I will write it on the right hand side. Okay, so I call factorial of 3. So also you have to keep a note of what is bold here, right? So when something I make it bold, it means the code, the interpreter or whatever, whoever is running the code is at that line, right? So when I call the function, I am at the topmost part, right? And when I reach this part of the code, what happens is that I am calling the function again, right? So it's 3 into factorial of 2, right? So we are currently in factorial of 3, but we ended up calling factorial of 2. So what we have to do is we have to suspend, or we have to temporarily stop the current function or current procedure. And that I signal using an LO. So did you understand what we did so far? So what happened in these last 2-3 steps?
Yes, sir.
Okay, so there is a function call or a procedure call. So whenever a procedure is running, whenever I'm inside a procedure, I make that green, right? That particular procedure, I make it green. the moment I call the procedure again inside it, right? So when I say 3 into factorial of 2, I end up calling factorial again. So now a new factorial gets created, right? A new procedure call gets created. So I have to suspend my previous procedure call. Okay, I made it yellow. Now what do you think will happen? What will be the return value for this case?
2 into factorial of 1.
2 into factorial 1.
Correct, right? So it will be 2 into factorial of 1. So this is now green, right? So I started from here and I came all the way till here. So this is what is returned. But now once again, I end up calling the function again. So, or the procedure again. So what will happen now?
1 into factorial of 0.
Before that.
So factorial 1. Factorial 1.
Correct, right? So a new entry will be added here, factorial of 1. And that's again, you start again from here. Now, what will this return?
1 into factorial,
1 into factorial 0.
Okay, 1 into factorial 0. And then we continue this. Finally, I reach factorial of 0. Now, what happens in factorial of 0?
It will
So
return 1.
factorial of 0 give us 1.
Okay, so it will return 1 because this if block will evaluate to true. Okay, so it will return 1. So now what will happen? Now, is this a recursive procedure call or is it not a recursive procedure call? See, all these calls, right? So remember, there are 3. I have made actually 4 calls here to the same procedure factorial. I made factorial of 3, 2, 1, 0. Out of these 4 calls, which of these procedures execution will I call recursive? Which of these is like not recursive?
Yellow color are recursive.
The yellow colors which are on hold, they are recursive.
Okay, so they all are recursive because they have called the procedure again, and this one is it hits what this is called the base case, right? So this hits what is called the base case of recursion. Every recursive procedure will have what is called a base case. Okay, so the base case is what? It is the position where the code doesn't call itself again and it will just stop, right? So that's what is the base case. So once factorial of 0 returns 1, we are done with it, right? There's nothing more to do with it. So that becomes red. Okay, so you notice this part being in bold now because we are done with factorial of 0, right? There's no more going back to that particular case. Okay, now what happens? This is where it might get confusing. There are 3 yellows, right? There are 3 procedures that were suspended that were in yellow. Now, which of these 3 will you take up?
So the backtracking would happen. Factorial 0, where it was called, it would go there first. Then after it's done, then where factorial 1 was called, it would go there.
Correct.
That means the way we end up to 1, it would follow the same path but backwards.
Correct, right? That's correct. So you will go back to that procedure call, from which factorial of 0 issued, right? So factorial 1 is the most recent one, right? It's the most recent one. So that will get activated again. And this part will become bold again, right? So this is where you are. In factorial of 1, you are at this stage when you call factorial of 0. Okay, so now factorial of 0 is what?
It's 1.
It's 1, right? You have already computed it. So we are just going to make use of this. So it becomes factorial of 1 becomes 1. Okay, now likewise, you called factorial of 1 from inside factorial of 2. So that is going to get reactivated. And since you have already computed factorial of 1, you will compute 2 into 1. So that becomes 2. And finally, factorial of 3 is the one which called factorial of 2. So it becomes 6. And the first call from which we started, right? It was factorial of 3, and that is the one which ends last. Okay, so this is roughly the structure of a recursive program. I'll just few points to make note of, which is that this is called a procedure stack or a call stack. So notice that I am stacking the procedures one on top of the other. So first there is factorial of 3. I stack factorial of 2 on top of this, like I stack books on a bookshelf, right? We have a bookshelf and then how do you keep books there? You keep one on top of the other, right? So likewise, this is called a procedure or a call stack. I keep stacking my procedures one on top of the other. Okay, and how do I take out books from a stack? I can't suddenly pull out a book from the bottom, right? I take the topmost book and then I take the one that is below it. Likewise, the way the functions end, the way the procedures end is by picking the topmost procedure. So I first take out this, then I take out this, then I take out this, then I take out this. Okay, so that's the overall idea of recursion. Any questions about this process?
So, sir, last in, first out concept, just like we used in stack. I mean, basic in programming stack, that thing, last in, first out concept, right?
Yeah, exactly. That's how this recursion is done, right? So this is factorial. So now let's quickly do one more example where you have a list and you want to compute the sum of the elements of this list. Okay, so let's go the same procedure. So let's say we have to compute sum of this list. Okay, now what will be the return value of this?
10 plus sum of 10
list.
comma 20. Sorry, 20 comma 30.
Okay, right. So I hope all of you see this. The first of L is 10 and the rest of L is nothing but the list containing 20 comma 30. Right. So that is the return. Now, where do we go from here?
New element will be sum of 20, 30.
Correct. Right. So this will be suspended and then you start with sum of 20, 30. So the return value for that is
20
plus
plus
sum of
plus
list.
30.
okay. So that is correct. Now here there might be a source of conversion, but anyway, so how will you do this sum of 30?
New element will be sum of 30 and sum of 30 is equal to 30 plus empty list.
Correct. It's correct, right? So sum of 30 is what? Sum of 30 is 30 plus sum of empty list. Now, what is the sum of empty list?
Return 0.
It would return 0.
We return 0, right? So we return 0 and then we just backtrack from whatever we computed. So this is the value of sum of the empty list. So that goes in 30 plus 0 is 30. So that gets computed and then 20 plus 30 is 50. And then finally we end up with 60.
60. Okay.
Okay, so this is how so that is how the list sum works. Now, next we have sorting. Okay, so again, I take up the same example that Professor Madhun has done and we go from there. Now, let's try to do this example of 51324, right? So now, so it's like let's now look at the procedure one line at a time. So is the length of L W equal to 1? No, right? So we go to the else part and we are returning a kind of several things are happening here, right? We are inserting the sorted version of the rest of the list, and that's we are inserting the first element of L into the sorted version of the rest of the list, right? So it's like several things are happening. So what do you think will be the return value of this particular?
So what does insert mean here?
Insert, what it does is, if you are given a sorted list, it will insert the second item into the list.
Okay.
Insert will do insert of L comma X is, it will insert X into L at the right place. Right? This is what insert will do.
Answer, it will be a list of 1, 3, 2, 4, and 5.
Okay. So it will be insert of, this is what this function is going, this procedure is going to return. It will insert, as you said, sort of 1, 2, 3, 4, comma 5. So did everyone get this part?
Yes, sir.
Yes, sir.
Okay, so this is what is going to return. Now, what will be the next recursive call? Next call?
Sort of 1, 3, 2,
Sort
4.
of 1, 3, 2, 4, and then 5.
Okay, so sort of 1, 3, 2, 4, right? But 5 will come to that later, but the recursive part is sort of 1, 3, 2, 4, right? So that's what will happen.
Yes, sir.
Got
Okay,
it.
now proceeding on similar lines, what will this be?
Insert sort 3 to 4
3 to 4
and 1.
and 1.
Okay, insert sort 3 to 4, 1. Next one is sort 3 to 4, which will be
Sort
Insert sort
2, 4 and 3.
and 3.
okay, and I hope you all get it. So I just continue. So the final stage, at this stage, what happens?
Length
Sort
is
of-
1, sir, so it will return L.
It will run.
Correct, right? So this base case, as we say, base case of the recursion kicks in, and we'll end up returning just the list 4. Okay, now we backtrack. So we are done with this. So this becomes 4. So this 4 is going to get inserted here, right? So sort of 4 is just 4. So what is insert of 4 comma 2? According to whatever I said about insert will
It's
just
going to give
2,
2, comma 4.
correct, right? 2 comma 4. So now sort of 2 comma 4 is 2 comma 4. So it has done its job. So now this will become active, and what will this turn into?
2, 3, 4.
2, 3, 4.
3,
3,
4.
2, 4 or 2, 3, 4, sir.
2, 3, 4, right? It's inserting 3 in the right place of
Yes, sir.
this list, right? So 3 will go between 2 and 4, right?
Oh, insert means the inserting it into right place.
Exactly. Yeah, that's what here in this case insert means that.
Okay, okay, sir.
Okay, so that's what insert.
Insert another procedure, sir?
Yeah, insert itself is another procedure which we have not written down here, but
Okay, sir, got it.
yeah. Okay, so that becomes,
Insert is inserting the inclusion.
insert is inserting the element 3 in the correct
Integer in a sorted list.
correct. Yeah, exactly. Okay, so that is 2, 3, 4, and finally this becomes what? Again,
1, 2, 3,
1,
4.
2, 3, 4.
right? Insert of 2, 3, 4, comma 1, 1, 2, 3, 4. Finally, you have insert of 1, 2, 3, 4, comma 5, which
This
is
will be 1, 2, 3, 4, 5.
okay. So this is recursive insertion sort, right? So this is a particular sorting algorithm called insertion sort, where you insert an element in an already sorted, in a partially sorted list, right? And you keep increasing the size of this list, and finally the entire list is sorted, right? So this is called recursive insertion sort. So you will study more about this in your diploma level, right? So when you go to diploma and you'll take up a course again by Professor Madhavan, which is called PTSC, right? So data structures and algorithms using Python. We'll study this, not just this, but several other sorting techniques. So all of them, not all of them, like quite a few of these sorting techniques use recursion. So you must be quite thorough with recursion. Of course, sir will again teach those concepts, but it's good to get used to recursion right now. Okay, so that's one set of slides I had on recursion. Now let's go to DFS. Okay, so let's go to DFS and then see what it has stored for us. Okay, so let's take an example. Now, let's say I want to explore this graph. See, DFS is what? It's a graph traversal technique. So it's a way to explore a graph. And that's what DFS is all about. Now, it's one way of exploring the graph. There are different ways of traversing a graph, and this is one such technique. It has its own uses. So we'll first look at how to explore this graph from the node 0. Okay, again, I use the same. I'll come to the code for DFS towards the end, but for now, let's just do a bunch of examples, right? So if I start from the node 0 and I want to do DFS, what will be the next step?
Either 1 or 3.
Okay, let's assume for the remainder of the session that we always, when you have a choice, you always choose the smallest node, right? Smallest in the sense, whatever label is smallest, right? So you have 1 or 3 and let's choose 1. Okay, so whenever you choose a particular node, the current node gets suspended, right? So keep the idea in mind. So this becomes yellow and node 1 becomes active, right? So also notice that since you reached 1 from 0, there is a directed edge from 0 to 1. Why is there a directed edge? Because from node 0, you went to node 1, right? So 0 to 1. Okay, so now what do you do next? Can we go back to 0?
So
No.
1 to 2.
It is
One
direct.
to two, sir.
Okay, there's only one choice left, right? Actually, there are 2 choices, but then you have already visited node 0, so there's no point going back there. So you go to 2. And what about 2 now?
We're going to 3.
So from 2 to 3.
Okay, we go to 3. Now at 3, there are no more choices left for us. There are 0 and 2, but then they are already visited. So at 3, the procedure stops. Okay, and so notice that very close ties this has to recursion. Okay, because we are kind of following the same coloring at least, right? So from 3, what happens? We go back to the point from which 3 was called. From where was 3 called? 2. So we go back to 2 and then we see that we cannot explore anything more from 2. 2 was called from 1. I go back to 1 and I see that there is nothing left to be explored from 1 also. Finally, I go back to 0, from which again I've spent everything, right? So I've explored the entire graph. Okay, and we are done. So this is called, what is this called? The one on the right.
Depth first search.
DFS tree.
Correct.
DFS tree.
DFS tree, depth first search tree. So it's a directed tree, right? So where the direction of the edges indicate the parent node and the child node, right? So you can think about this as parent and child relationship, where if node 1 was explored from or first visited from node 0, then 0 becomes the parent of node 1, and one other way of saying this is that 1 is the child of node 0. Okay, so this is a DFS tree, and DFS tree is a directed tree. Okay, that's example 1. Does anyone have any questions at this stage?
So DFS tree is always a directed tree, right?
Yes, yeah.
Okay.
Okay, so we'll go to example. Before we go to example 1, notice that the DFS tree has 3 edges, whereas the original graph has 4 edges, right?
Oh,
So
yes.
this particular edge connecting 0 and 3 is not a part of the tree. Okay, it's not a part of the tree. That's but I've just drawn it for completion. Okay, so in general, you don't need to draw that. So that particular edge is not a part of the tree. It's not a tree edge. It's just one of the edges from the original graph. But that just gives you an idea of which all are part of the tree and which all are not a part of it. Okay. Okay. So can DFS be done from only node 0?
No, sir.
So we
So,
can start
we can start from any node.
Okay.
Any node, yeah.
Okay, so we can start from any node, right? So let's just very quickly go over the same graph, but we are starting from node 3. So what will be the next node?
Zero.
0.
Zero, sir.
Okay, next one is
1.
2.
and then 2.
Okay, right, and then I just keep going back, and we are done, right? So the 2 things from the previous example is that DFS will produce a DFS tree, and you can start you can start your DFS from any node. Final point which I didn't mention is, if you end up visiting every node from any given node, right? So let's say you started DFS from 3 here, and you were able to visit every node of the graph in the process, right? You started from 3 and you were able to explore 0, 1, 2. Okay, those are the nodes in the graph. So what can you say about such a graph?
So it's a connected graph.
Correct, right? So
Because I can reach, I can reach every vertex or node from
Yes, sir.
particular
I
one
can
node.
reach
So it's a
from anywhere
connected
to
graph.
anywhere.
right. So what does DFS help us do then?
Teachability.
To find out the path from which path we can go from one node to another node.
Okay, but at a more abstract level, about the graph, what does it tell us? In just whatever we discussed just now, can DFS be used to determine something about the graph?
Teachability.
Okay, reachability. All right, that is one thing.
Reachability and the number
So
of
if
edges.
the graph is connected or
the
not.
minimum number of edges it requires to connect.
Right. So if the graph is connected or not, right? So DFS will tell us if the graph is connected or not. More interestingly, and in fact that's the most interesting part, but more importantly, it will also give us how many connected components are there. So we'll discuss this in a bit towards the end of the session. We'll take up a different example and go over that, right? So for now, just keep this in the back of your mind. DFS gives you a way of understanding which nodes are reachable, and overall it gives you an idea of whether the graph is connected or not, right? So, and if it is connected, sorry, if it is not connected, how many connected components are there? So we'll spend a brief amount of time on connected components towards the end. Okay, but for now, let's just continue. Okay, so let's do DFS one more example for a slightly more complex looking graph. We'll start from the node 3. Okay, so can we just quickly go over it? What will I do next?
Zero.
Not
three
one.
to
Go to zero.
Not zero. Not
One.
zero.
Zero.
Oh, sorry, 0, 0, right. 0.
Zero.
Yeah, next.
5.
5.
5.
Okay,
0 to 5.
1.
1.
1.
1.
5 to 1.
4.
1.
4.
4. 4.
Again
Now
3.
go back
No,
to
no.
Go back.
Go back.
Go back to 1.
1.
Go back to 1.
Go back to 5.
Go back to 5.
5.
okay, go back.
Then 2.
Go back.
And then
2. 2. 5
It
to
will
2.
go to 2.
5 to
5
2.
to 2.
Okay,
Go back again. 5.
Go back.
Go
2
back
to
to
5. Go back to 5.
Then again 0.
oh, why not? Why can't it go back to 3?
So 3 is seen already.
Three.
Already seen, sir.
5 is the parent of the 2. It will go to
Okay, right. Yeah. So it has to go back to the node which called it, and since 5 is the one which called it, you go back to 5. Okay.
5.
What?
Then 0.
0,
0.
Three.
Then 3.
And then 6.
6.
And then 6.
then 6, right? So that's the DFS tree of this particular. So how many non-tree nodes non-tree edges are there? Does it account for all the edges, or are there any edges which are not present in this graph on the left, but not present in the tree?
3 to 1.
3 to 1. Okay, that is one edge. Is that all?
There is
0 to 6.
Sorry, sir. I didn't understand your question.
So there is, see, for example, there is this edge from 3 to 0. No, that gets accounted here, right? 3 to 0.
3 to 1 and 3 to 4.
Right. So, like, what I'm asking is there any edge in the original graph which is not present in the depth first search tree? For example,
3 to
Right.
3 to 1 and 3 to 2.
3 to 1, 3 to 2. Okay.
3 to 4 also.
3 to 4 also.
3 to 4 also. Okay. Okay. So let's
2 also, yeah.
correct. Right. So those are the 3 edges. So these are not the tree edges. These are part of the original graph, but do not feature in the depth first search tree. Okay.
Yes.
So again, a minor point, but just note for completeness sake. Now, is this graph connected or not?
So it is connected.
Connected, sir.
Connected graph, yes.
You visited all vertices. So great, right? So yeah, that's the nice point. Right? So you have to see this in both cases, right? So the graph is connected, and you are able to visit all the vertices starting from 3. So that is one thing. So if I were to do the DFS from 1, will I still be able to visit all the vertices?
Yes, sir.
Yes, sir.
Yes, sir.
Right. So that's
Yes, sir.
different part, right. So you'll be able to visit all the vertices or nodes, no matter from where you run the DFS. Okay. So, all right. So let's now start going into the code of DFS. Now that we know very clearly what DFS is doing. Okay. So let's first complete the adjacency matrix for this particular graph. Right. So let's go row by row. So is there an entry? Okay, there will be an entry for every cell here. So 0, 1, 2, 3 is the index for a node, right? And so 0, 0, graph of 0, 0. What will be the value of graph of 0, 0?
0.
0, 0.
Okay. Likewise, can you tell me for this entire row what will be the 4 numbers?
0, 1, 1, 1.
0, 1, 1, 1.
Okay, that's correct. So 0, 1, 1, 1. Okay, does everyone
Sir,
understand?
how it happens, sir?
Okay, so there is first row is what first row is telling me this following information from node
Yeah,
0.
I got it, sir. Yeah, it is connected, so it is 1. Yeah.
Ah.
0 to 2 and 0 to 3, 0 to 1. Yeah. Okay, sir.
Correct. Right. So is there anyone else who is having a problem with adjacency matrix at this stage? Because we plan to discuss this, right? So if you have any questions, please ask them now. Okay. I hope. Okay.
Sir, from coding point of view, I have to understand.
Okay. Yeah, we'll come to that, right? So now from second row, what will be the second row?
1, 0,
1, 0, 0, 0.
Okay, that is correct. What about the third row?
1, 0,
1,
1, 0,
1, 0, 0,
1,
1.
0, 0, 1.
1, 0,
1.
Okay, and final row?
1,
1,
0, 1,
0, 1, 0.
1, 0, 1, 0.
Okay, right. So that is correct. So that's your adjacency matrix. Now we can start our DFS, and according to our core algorithm, what we need is an empty dictionary, right? So we need an empty dictionary and we are calling it visited. So initially it's empty. So don't ask me why I have 4 entries here. I know that I'll end up with a dictionary with 4 keys and 4 corresponding values, but in general you don't know, right? So this will not have any entries here. So please treat this as an empty dictionary. Now visited is there and you have graph. So those 2 are already there. What else do I need to call the procedure DFS? Can I call DFS now on graph and visited? I need a starting node, right? So I need a starting.
Yes,
So let's say we do DFS on this graph with this empty dictionary visited, and we do DFS from 0.
0.
Okay. Now what will be after the first line is executed, what will happen to the
key 0 will be
0, true.
having true value.
Okay, right. So the key 0 will have a value true, and we are now in the node 0, right? So we are in the node 0, we are exploring it. Now let's go to the for loop. Okay. So I've just made this bold to represent that we are inside the for loop. Okay. So we could be anywhere inside the for loop. So we are asking this question. I've just pulled out this if condition, and this is the if condition, right? Whatever is the condition inside the if block, I have just pulled it out here. So can someone tell me in words what the first part of the if condition means before the end? What does this mean?
Or it will check
First
for
part is
each column.
not true. So this condition will not apply.
It will check for each column. It will check whether the value for each column in row 0 is 1 or not.
Okay, it's in terms of column and row. Can you tell me in terms of the graph?
Okay.
Graph?
It will iterate through all vertices.
It will check whether we can reach from 0 to that particular node or not.
Okay, now, yeah, that's right. So I'll take that. So what is the first part of the if condition stating? It's stating the fact that it's asking the following question: does my node 0 have an edge with my neighbor j? Right. So is j, or in other words, is j? Can I call node j my neighbor? When can I call a node my neighbor?
If there is an edge.
There is an edge.
There is an edge.
Okay, so in terms of the matrix, when is there, if there is an edge between 0 and j, what is graph of 0j?
The
One.
value will be 1.
Value is 1, right? So this is the amount of logic we are building into this one statement, right? So graph of 0j w equal to 1 is simply asking the following question: is j my neighbor or not? So I am 0, assume that I am 0. Is j my neighbor or not? If j is my neighbor, then what can I say? Then I can say that j could be a potential person to go to next, right? I could start exploring j next. Okay, that's why we asked this condition first. Now, that is good enough, right? Why do I need this extra condition connected by an and?
We want to see whether we have visited
We are
that
checking
or not.
if we have visited J or not.
Correct, right? That's correct. So just recall in case you are not. So let's say we were at, now let me quickly go. So we were at 5 and we then went to 2, right? Now, ideally what the for loop would have done, it would have checked 1, right? But since 1 is already visited, it didn't go there and it went to 2, right? So since 1 was already present, it didn't go to 1, right? It went to 2. So that condition we need to check. It's not enough if there is an edge between 0 and j. You should also check if j has been visited.
Already visited or not.
Okay, so how is this done? So is key of visited comma j? Okay, so is key of visited comma j? So is j present in the keys?
Visited, yeah.
Okay, so we have to do this for how many values of j? We have to ask this condition for how many values of j? 4, right? So we have to ask this for j equal 1, 2, and 3. So that's what the whole loop is about. You are going to loop from the you are going to loop through the columns of the graph. What are the columns of the graph? 0, 1, 2, 3.
0,
Right?
1, 2, 3.
So for each value of j equal to 0, 1, 2, 3, you are going to ask this question. So let's ask this for j equal to 0, right? So is graph of 0, 0 w equal to 1?
No, it is
All right. So there are no self loops. We call this as there are no self loops. And 0 is not connected to itself, right? So if this is false, do I need to check for the second condition?
No, sir.
No, sir.
Okay.
It's an and, so we don't need to.
So don't need to check. So let's go to j equal to 1. So is the first part of it true?
Yes, sir. It's
Yes, it
fulfilled.
is true.
Okay, so there is an edge from 0 to 1. Therefore, this is true. Now, what about is key not of is key visited comma 1?
It is also true.
It is
That is
also
also
true.
since one we just visited.
Correct,
It wasn't
right?
visited before.
So 1 is a key of visited. No, 1 is not a
No,
key. Right? So not of this will be true.
True. Yes, sir.
So what happens now? We have to make a recursive call. So this we go inside the if block. We make a recursive call to DFS of graph comma visited comma what? What will be the value on which 1, right? So I make the next call to DFS of graph comma visited comma 1.
1. Okay.
Okay, so did everyone get this? Is there anyone who wants this to be repeated? Please stop me here, otherwise I'll move on.
Yes, sir. Repeat, sir.
Okay, so can you tell me which part you didn't was unclear? So this part was clear. This first if condition.
Yes, sir.
Okay, so is this part clear? This is key of visited comma 1.
You have to come.
Okay, so see here what's happening is we are asking if 1 is a key of the dictionary visited.
It's not.
It is not, right? So is key of visited comma 1 is asking the question, is 1 a key of visited? No, this is not a key. Okay, so is key of visited comma 1 will be false, right? Because it's not a key, it is false. So not of false will be true, right? So that is how this also becomes true.
Yes.
Okay, so once both of them become true, I go inside and I end up calling DFS on the graph with this dictionary currently and on the node 1. Okay, so I suspend this, I enter 1 and visited of 1 becomes true. Right, so a new key is added to the dictionary because you started DFS here. Okay, so and then you repeat the whole process. Now, what happens to graph of 1 0?
It's true, sir. It's 1.
Okay, so shall I go and visit it? Can I do DFS of graph of visited comma 0 again?
We will check for the next part of the condition, whether it's already present or not, for value 0. But if it's already present, so we will not be executing this.
Correct, right? So now we are checking if 0 is a key of visited, 0 happens to be a key. So this key is going to evaluate to true. So not of true will become false, and therefore the entire AND condition, this whole if condition will become false, right? So we are not going to visit 0 again. So I'll just skip this. Okay, I'll just skip this. And do you all see why this has become red now? Why we reach the end of DFS?
Yes.
Okay, so anyone wants to explain why we reach the end of DFS?
Because all of rest J we are having 0 for the first part.
Correct, right? You are right. So for all the other values of J, so we tested J equal to 0. 1, of course, there is no edge. For 1 to 0, there is an edge. For J equal to 1 to 3, there is anyway no edges, right? There are no edges. So this if condition will not be satisfied. Okay, and we'll just end up returning visited. Okay, now what? Now where will we go back? So
we will go back to
Visited
1. So visited 0.
yeah, we go back to visited 0, right? And we'll continue from where we left. So
Yes.
in which column were we in?
Not coming.
So remember, so can you tell me which row and which column we are in currently?
0 and 1. Now we go to 0 2.
Correct, right? So we were in 0 1, and that is where and it was from there that we had called DFS graph visited 1. So now we'll go to column 2. So what happens?
It will make an entry for visited 2 as true, and then we go to it will check the if the value is 1 or not.
Graph of 2 and 0, and it will be true, but the second part will be false because 0 is already visited. So the given statement will not imply for the first column.
See, 0 2 is there at the edge. So we are going to check for graph of 0 2. So that's going to be true. 0 2 is 1. But is 2 a key or visited?
No, sir.
Okay,
No.
so I can go ahead and call graph DFS on that, right?
Yes, sir.
Okay, so that's what is going to happen. Now, what will happen now to visit it if I start executing DFS graph visited 2?
So it will make a key value pair for 2, and it will value will be true for 2. Then it will go to the for each j in 2. So it will check for 0 first, and it will check whether the value is 1 or not, which it is value 1. And then it will check for that j for 0, whether the key is already present or not. And since the key is already present, we won't be executing the if part. And then we go to the next column, 1. It will check whether the value is 1. It is not, so we will not be executing it. Similarly, for 2 also we will not be executing. Then we go to 3. For 3, the value would be 1. And since we have not visited 3 already, there's no entry for that key value entry. We will be calling DFS again for that.
Okay, that's correct, right? That's correct. So we are now going to, as you said, we'll be checking for all the columns 0, 1, 2. We are checking, and now we are checking 3, right? So graph of 2, 3 is there. So 2, 3, there is an entry, and 3 is not a key. So we are going to go ahead and visit the third node, right? So we'll suspend the second node, we'll visit the third node. Now, what will happen to visited dictionary?
So 3 will be the key with having
3 will key
true
2,
value. Yeah.
2.
Right.
Then we go to each column. But since we have already visited each column, it will not execute.
Right. So what will happen to DFS graph, visited, 3? How should I color this now?
Red.
Red.
Okay, right. So I'll color this red because there are no more recursive calls here. I'll end DFS. Now 3 will go off, and what will become green now?
DFS graph visit 2.
Okay, it will be 2, right? So that becomes active. That again, you have already visited everything. So you are going to come out of the for loop, return this dictionary, and then
for 0.
Right. So finally you are at 0, and so remember you had one more node to check, right? You had to check 0, 3, but then 3 is visited. So there's nothing else left to do, and you end up with this particular dictionary, right? So did everyone get this sequence of steps that we followed? Are there
Yes,
any?
sir.
Yes, sir.
Yes, sir.
All right, right. So that is one more set of slides I had. I also have one more on recursion. Let me pull that up. So okay, so I'll be discussing some of the practice assignment questions. Okay, so
Sir, in the last example, we found the recursion procedure. We did the recursion procedure, but we didn't get the graph. DFS tree. Yeah.
Good point. Yeah, that's a good point. So there is a way to modify the code such a way that we can get hold of the DFS tree also. Can you tell me what modification you would have to make?
Sir, actually, I have not watched that video, sir, so I don't know.
Okay, so maybe let's do that now. Let me share this particular screen. Let's do this and then go back to these practice assignment questions. So are you all able to see the screen that I'm sharing?
Yes, sir.
Yes, sir. Yes, sir.
Okay, so let's start with let me make the font size slightly bigger. Okay, so I'm now writing this procedure DFS. Okay, maybe this is also an good exercise to see how code is written from scratch, right? Let's write this code from scratch. Now you have a procedure DFS. Now I pass the visited dictionary. Pass the graph first, and then I pass visited, and then I pass the node. Okay, so then somewhere below I end DFS. In between this, I need to write my code. Okay, so as usual, I do this part, right? If I, in fact, I don't write the base case first. I'll do the recursive part first, right? So I go through all the columns in for each chain, columns of what?
Columns of graph.
Okay, so for each chain, columns of graph, this will give me a list of columns. Now I ask this question: if graph of ij
equal to 1,
equal to 1, right? And
not visited.
okay, yeah. So let's look at is key of visited.
Visited.
I. Sorry.
And
Okay, if this is a key, then I should not go, right? So if this is a key, this will evaluate to true. So not of this,
not is the
right? So not of this. Now, if this happens, then what do I do? If this happens,
we call DFS.
I call visited. We call DFS again on graph visited on J, right? And then
Okay.
in the end we return visited. So visited. Of course, we close the if block. We close the for each. Then finally we have to write this part, right? If there's no if, but
Visited I true.
okay, so this is what happens, right? So this is the code that we have. Now the requirement is I need the question that was asked. It's actually an interesting, very good question. I don't have access to my parent nodes, right? So I don't know from where I came. I don't know where I came from. So if you have a graph, you know what all nodes were visited, that's fine. But if you want to reconstruct the DFS tree, okay, I don't have a way to do that here. Okay, so one way to plug that is when you are going to call DFS on visited, right? So, on J, you can do the following. Let me know if this makes sense. Visited of, we'll probably have to keep track of something called parents, right? So the root, so do you all understand what I mean by a root node?
Yes, sir.
Okay, so let's say I'm calling DFS from, so parents is an empty dictionary. See, I'm like a bit rusty on CT syntax. How do you create an empty dictionary in pseudocode?
We assign it
curly
to
braces,
curly
leaving in
braces.
like this.
Okay, fine. So let's say I want to do DFS from the root node 0. Let me quickly draw that so that we don't forget. So we understand what we're talking about. So let me have a node 0. Okay, so this is a node. We'll take a very simple case of 0, 1, 2, 3. Okay. So this is 1, this is 2, this is 3. So this has a node, this has an edge, this has an edge. So does this, and so does this. They're all directed edges, and I want an undirected graph. So I'll just turn this into undirected graph, right? So if I do DFS from 0, then I have 0, 1, 2, 3, right? So I just have this. Let me just draw this. So this will be 0, 1, 2, 3. Okay, this will be the DFS tree. I'll make this 1 and I'll make this 2. Okay, so finally let's see what we want. If I have a dictionary called parents, I'll just write down the dictionary. That's the specification. Then let's go back, right? So 0 will have some parent, 1 will have some parent, 2 will have some parent, 3 will have some parent. Okay, so that's the dictionary. Now, for the root node, what do you think would be the parent?
For root
Null cell.
node, I mean,
No parent.
I mean, basically we take root node which doesn't have any parent actually.
Right. So there's no parent, right? Well, let's just make it -1. Okay, let's just make it -1. -1 will denote the fact that the root
It
node
has
doesn't
no parent.
have any parent, right? So what should 1 have? What is the 0, right?
Zero.
0.
For 2
2
we
has 1
1,
and
3 has 2.
2.
okay, this is what we desire. Okay, this is the desired outcome is that I need, once I do DFS, I need to have a dictionary like this, and I need to have a visited nodes dictionary like this, which will of course turn out to be something like this, right? So this is the desired outcome. Now we need to write a code that reflects this. Okay. So what I'll do is I'll initialize parents to be an empty dictionary, and parents of 0, let's say I start DFS from 0, should be what?
-1.
It should be -1. Right? So once I call DFS, now, of course, visited of I is true, that's fine. Now, when you are calling DFS on J, what line can I add here?
Parents J equal to I.
Okay, that's good. Will this work? Shall we just think about it for a while? Will this work correctly? And is this enough if I return visited, or should I return something else? I need to return both.
Parents
Both
also.
parents also.
Okay, so this is like a DFS where I call graph. I call it on the graph on visited, and I also include the parents. And I end up returning this. So let's quickly run this on this and see what happens. Now, for this particular graph, what will be the matrix? So I'm going to write graph. Graph is nothing but adjacency. This is the adjacency matrix, right? So yeah, that's a nested dictionary. That's correct. Now nested list, but okay, how do you define in CT nested dictionary or nested list? Again, I'm kind of rusty on
So it's a
pseudocode.
nested dictionary.
Nested dictionary, sir.
Thanks. Okay, right. So this is a nested dictionary, but from the mathematical standpoint, what will be the adjacency matrix? So 0, 0, 1.
0, 1, 2, 3 column and 0, 1, 2, 3 rows.
So it will be what? How many rows? How many columns?
4 rows and
4 columns.
4 columns.
4 rows, 4 columns, right? So what will be the first row? 0,
0, 1,
1,
2, 3.
0, 1. Is that correct?
So you're asking for the edge value, right? You're not asking for the index value.
Yeah, the edge value.
Okay.
0, 1, there is no edge from 0 to 2. There is an edge from 0 to 3. Okay, what about the second row?
1, 0, 1,
1,
0.
1, 0,
1, 0.
Okay, what about the
0, 1,
0, 1, 0,
0,
1.
1.
Okay, finally
One,
Zero,
One
zero,
zero,
one, zero, 1, 0.
1 0,
1
1 0.
0.
Okay. Okay. So this is what you have. So the input is, what is the input that you give? You give graph as an input, and as you said, there's a nested dictionary, right? So 0 1 0 1. So this is
Two
what,
values.
this is true false, right? Is that how it is?
Yeah.
Okay. So for 0 it is false, right?
Yeah.
So for 1 it is true. For 0 it is false.
So, yeah.
Sorry, 0 1
0,
2 3.
2, sir. 2, yeah. For 3
Okay.
it is true.
Is that correct?
So the values would be 0, 1 in those, in that case. It will be, instead of false and true, it will be 0, 1.
Oh, it is 0 1, is it? Okay. So
Yeah.
okay, it is 0 1.
1, 0,
0.
and 1.
Okay. So this is the dictionary. Is that correct?
Yeah.
Yes.
And then we have 1 as the another key.
Another
Okay.
element is 1.
Okay. So let me just, sorry, 1 second. Let me just duplicate this for all 4 nodes. And then we have
2, 3. Yeah.
so is what 1 0 1 0, right?
1, 0, 1, 0.
1 0 1 0.
And 0, 1, 0, 1 for the next.
0 1, yeah, it is correct. And
And
1
then
0.
1, 0, 1, 0.
Okay. So 1 0. Okay. So that is, this is the input, right? So this is what we give as input. And of course, visited is an empty dictionary. That is what we give as input. And parents is not an empty dictionary. We give parents of, okay, anyway, we or no, it's an empty dictionary, and this is where the code, assume that this is where the code starts, right? So one aspect of code. So parents of 0 is -1. Now, yeah, now we have to execute this and figure out if you are doing the right job. So for ease of understanding, let me put this side by side, or at least here. Okay, so I'm going to keep updating this dictionary itself in place, right? Without having to create a new one every time. So when I am going through zeros -1.
-1.
Yeah, now let's start DFS. So instead of I is true. So what will be
0
the first?
is true.
Okay, that is done. Now we'll go
For
through
each column.
this.
First 0, which would be, value would be 0, we will not execute. Then we will check for 1. It is 1 and it is not a key that is present in visited. We will call DFS for it.
Okay, so parents of what equal to what? So what will I?
1 would be 0. Parents 1, 1, 0, 1, 0.
Okay, so 1 0. So that gets added, and now I go back. I call DFS. I am now in DFS of graph comma visited comma parents comma 1, right? So what will visited change into?
1, 2.
Okay, so from 1, do we have anything?
0, 0 is 1, but it is visited already. So then we will go to 1, which is 0, we will not execute it. Then we will go to 2. Parents 2 will be 1, and we will call DFS for 2.
Okay, parents 2 will be 1, right? So parents of 2 equal to 1, and we will call DFS on 2. Is that correct?
Yes.
Okay, now we go to 2. This particular
2 will be visited. So 2 will be visited true.
2 will be
Necessary visited, yeah.
okay.
Then we go to 0. 0 for 0 value is 0. We will not be executing. For 1, the value is 1, but it has already been visited. We will not be going there. For 2, the value is again 0. We will not be visiting it. Then 3, the value is 1 and it has not been visited before. So parents 3 would be 2. And we will call DFS for 3.
Okay, done. So we are now in DFS of 3. So
Visited 3 would be true. And we will check for each and it will reject each. So we will return, we will end the code there.
oh, right. So we'll end the code there. So that is good. Now this is what we expected. This is the desired outcome, and what we have here is exactly that, right? So this will give you the parents of the DFS. So using this parents dictionary, you can recover the DFS tree. Okay, so basically, if you want to identify the root, what will you do? You will look for. Okay, let's consider this sub problem. Okay, given, let me ask this question. Given the parents dict, identify or write. So sorry, write that pseudo code to identify the root node. Okay, let's quickly write this code. So
for each keys of parents, for each k or in keys of parents,
okay,
if k, if parents k equal to -1,
okay,
return k.
all right. That is all right. Okay, nice, very nice. So let's call this procedure find parent. Okay, find parent. Sorry, find root. Okay, find root, and you just need the parent. Okay, and find root. Okay, so did everyone get how this was done? How we found out the root node? Okay.
Yes, sir.
Okay.
Yes, sir.
So we found the root node, and then of course, once you find the root node, parents of 0, so you can keep adding the parent every time you encounter a child node, right? So
This procedure is for the finding root of the parents only, no? Not
this
for
is
the
only for the root. Yeah.
Okay.
Okay. So now let's go back to few more recursion problems. I'll just quickly do the practice assignment problems, whatever we have. Okay, so there is this question on
Finding out the DFS tree is not a part of our syllabus. Using the graph.
DFS tree
using the code.
Sorry, I didn't get the question.
Sir, finding DFS tree using the pseudo code is syllabus part of syllabus or not? For
it is part of syllabus, yeah.
Okay.
Okay, so now is this has everyone seen this problem in the practice assignment? Finding the unique numbers in a list. Okay, so we'll do that now. There's a small variation which we'll do, right? Now there are. Okay, so can someone tell me what? So the unique procedure, I'll tell you what unique procedure is. Unique is a procedure which accepts a list of numbers as input, and it will return the distinct elements, right? All the distinct unique elements in the list by throwing away the duplicates. Okay, that's what unique will do. Now, can you tell me what will be the output of this procedure?
1532.
Okay, 1532. Okay, yeah. So, are we all agreed? Is there anyone who disagrees with this particular output? Is there anyone who has a different answer? Is this the only possible answer?
So,
does this question have only one correct answer, or are there other possible answers?
Sir, 2531.
The sequence may change.
Okay, sequence may change. In what sense?
From last element, we can start 2531.
2531. Okay. All right. So you just look at 1532 and tell me what you have done. You have done something, right? You have in giving me the answer as 1532. All of you have done something.
Shouldn't it return 2?
Shouldn't it return? Why?
Unique. Okay. No. Okay. Got it.
It is already present. We
Yeah,
remove
got it.
the list.
Okay. Going back to my question. Now you all did something when you selected 1532. What did you all select?
It's in the same order of the input list.
Okay, that's a starting point. It's in the same order. Now is can you think a little more and specify exactly what you have done? You have all actually followed an algorithm.
So we took the first of list and we checked for the rest
Duplicates.
DFS. We follow DFS.
DFS.
Okay. I mean, correct. So I just want you to spend some time now and tell me a different answer for the same question.
2531.
Not really. So okay. So let me tell this. So how many times does 1 occur in this?
Twice, sir.
It occurs twice. Now, can you tell me which one this is? Is it this one or is it this one that you have retained?
The
First one.
First one.
last.
Okay, so you have 2 5s occurring here. Which 5 have you retained? Is it the first 5 or the second 5?
The first one.
First one, sir.
Can you now tell me in a single sentence what you have chosen as the unique elements?
That is seen, sir.
First
Seen.
occurrences of each
Seen.
element.
Seen and also.
Okay, so you have retained, when looking from left to right in the list, you have retained the first occurrence of each element. Do you all agree?
Yes, sir. Yes, sir.
Okay, you have retained the first occurrence of each element. Now, with this prompt, can you tell me a different answer to this same procedure?
Yeah, the visited one.
Okay, can you tell me the final list that you will get? See, what else can I do? If I can take the first occurrence of each element, what if I choose the last occurrence of each unique element? In that case, what will be the output of this list, of this procedure?
1352.
So it would be 2, 3, 5.
Sir, can we
Sorry,
stop
1,
it?
2, 3, 5. 1, 3, 5. 1, 3, 5, 2.
Yeah,
Can you
1,
come
3.
again? Or what is the final answer that you're all telling me?
1, 3, 5, 2.
1352.
Okay, same list, 135, right? So that's correct. No, what we have done here is 1 is already there. 1 is going to occur again. So I'm ignoring this 1. 5 is going to occur again. I'm ignoring this 5. 3 is also going to occur again. I'm ignoring this 3. But this 1 I have to include. So I include 1. This 2 is going to occur again. So I ignore 2. This 3 I have to include. So 3 goes here. 5 and 2 anyway have to occur. They have to be plugged in, right? So this is 135. Okay, so there are 2 ways of getting the unique elements. When you're looking at the list from left to right, you could either retain the first occurrence or you could retain the last occurrence. Okay, now we are going to write the pseudocode, the recursive code for both these cases. That's what we are going to do now. So let's start. Let's do this for the second case, right? 1352. 1352 was the second one, yeah. So now assume that you have this list and you have to produce this particular output. So how do you think we can proceed?
Check with the length of the list.
Okay. Think about the recursive case first, then we can figure out the base case, right? So think about how do you think about the recursive case?
Length less than or equal to.
Is member of.
Yeah, we can use one more list. And
Okay, I'll take that. We'll use one more list, right? So what we'll do is whenever you think of recursive problems, right? So in general, it's also for the future. When you take up more complex you deal with more complex algorithms like in the PDSA course, right? In the data structures algorithms course, recursion usually comes in when you try to break the original problem into smaller problems that look similar to the original problem, right? So remember that you are trying to you are trying to find unique elements in the list. So it makes sense to break down the list into smaller lists, right? So what I've done is ABCAE is a list, okay? It has 5 elements, ABCAE, and I have broken it down into 2 smaller lists, okay? Of course, one is just a singleton list, meaning it has only 1 element, so it's not a great example of breaking things down, but still. Now, once I have broken this down in this way, can you tell me how to proceed from here? First of all, what is
If
interesting?
A is an element in the rest of the list, we can ignore A.
That's good, right? So if A is present in the rest of the list, you can just ignore this particular A, right? So that's exactly what I've drawn here. A is present in rest of the list, right? Rest is what? First is you keep the first out and then you consider the other elements. So A is present. Therefore, what do? I don't need A, right? I can ignore A and then just treat unique of BC
as a new list,
right? That will be the return value. Okay, so what will be the code for this? What will be the pseudocode for this? Just this
If
part.
he is not a member of the list rest of unique, then
If
we
member
have to start this is that number A.
is member, rest of list, and first of list. Then
Okay, then return what?
return rest of list.
Append unique.
Then return
with
list
the
rest
first
of
element.
list.
Okay, so let's break.
Return unique or rest of
Then
list
unique
first.
of list of.
Yeah, that's the catch, right? You have to return the unique of what?
Rest
Of list.
Rest of list.
Okay, right. So if the first element of L, I'm calling L as the list here. If first element of L is a member of the rest of the list, then what do? You throw away the first element. You don't need it because it's anyway going to occur in the rest of the list, and you are only interested in retaining the last occurrence of A, right? So you just return unique of rest of L. Okay, so this is what you have done is you have figured out one part of the logic. So you have broken down the list into 1 element plus rest of the elements, and you have considered one case where first is there in the rest. Now, what is the other case? First is not there in the list in the rest, right? So consider a case like this: A, B, C, D, E. A is not a part of B, C, D, E, right? So this arrow doesn't mean just this element D, but it means that A is not there in the rest of L. Now, how will the pseudocode for this be?
We have to add else statement and add
We have to append that to new list.
first element to the list. Rest of unique list.
Append
L plus
that element in the new list.
Okay, so where do we append this A? Shall we append it? Shall we add it to the end of this unique of rest of L?
We can make a new list.
Okay, but
And
At the beginning, sir. It should be at the beginning.
Should be at the beginning, right?
So we can do like return A and then plus unique of again like a unique of rest of them.
Exactly, right? That's what we'll be doing. So we'll be finding the unique of the rest of the list, and then we'll be adding or inserting A at the beginning, right? So that's the pseudocode for this, right? So I've not used else here. I will use else subsequently, but here if I just write else, it will be inappropriate. So I'm just writing it as if the first element of L is not present in the rest of L, then do this, right? So A has to be present in the final list, right? Because this is the only occurrence of A. So first of L, I have to add it plus unique of rest of L. So did everyone get the logic?
Yes, sir.
Okay, so now let's. Yeah, any questions? Okay.
Sir, in this case, unique, the remaining list of remaining member of the unique will have the unique value only.
Yeah, that will recursively find the unique elements in rest of it.
Okay, sir.
Okay, so now let's go on.
So when we call unique, will it return the first occurrence of that in the rest of list, or the last of occurrence of that?
Last, right? That is what we are trying now. This
Okay.
is right? So we are now taking the last occurrence. We are solving that first. Next, we'll look at the first occurrence problem.
Okay, okay, got it.
Okay, so here's a general procedure. Okay, no, not procedure. That the term procedure will again confuse. So it's not a maybe you can call it a suggestion. Whether you follow it or not is up to you. So, but when you work with recursive procedures, right? When you're trying to write a recursive piece of code, usually it's better if you approach it non-linearly. So what I mean by non-linear is you don't start from line 1 and then go up till line 10. Okay, that's not the way you write code in general. Okay, so even though you read code linearly, starting from the first line and go all the way to the last line, when you actually start writing code, which you'll do next term, right? When you take up Python, you'll figure out that usually you don't write code linearly. It's not like first line, I know exactly what to write. Then you keep going on and on, right? Things don't happen like this. Especially in recursive problems, it's easier to write the recursive part first. Okay, that's what we're going to do now. What have we done?
Condition part.
Yeah, right. So it's easier to write that first because the base case comes later. Okay, so even though the base case, when you're reading the recursive code, it comes at the beginning of your procedure. When you're writing a code, it is more appropriate to insert the base case right at the end. Okay, so that's what we have done here. So if the first element is there in the rest of the list, you just throw away the first element. Else, you append or insert the first element to unique of rest of. Okay, now you have done your recursive part. Now you've solved that problem, and you have enough mind space to look at the base case. Now, what is going to be the base case?
If length of list is less than equal to 1, return the list.
Exactly, right? So if you end up with a singleton list or an empty list, then you just return the list. Okay, there is a list with just one element. Obviously, that element has to be unique, no other go, right? So you just return the list. Okay, so this is the suggestion. Maybe you can keep this in mind when you start writing code next term, or if you are writing code for CT itself this term, it's a good procedure to follow, right? So even though you read code from top to bottom, sometimes when writing code, it's more natural to write certain parts of the code first and then plug in the holes later. Okay, so let's quickly evaluate this on this list. So what will be the return value for this? Is first of L there in the rest of L?
Yes, sir. One is there, yeah.
Yes, sir. It will return unique of the rest of L. That is
correct, right?
It will return 1, 3, 5, 2.
Yeah. So it will, yeah. But before we go to the final, let's just finish this. So is 5 there in rest of L?
Yes, sir. It's there.
So this will just return unique of rest of L.
rest of L.
Again, unique of rest of L. Again, now what will it do?
It will append the one.
Yeah. So just one
Rest of L.
small change. So
Yes.
append, the word append is usually used when you're adding something to the end, right? So let's call this insert, right? So it will insert 1 to the beginning of unique of rest of it. Okay.
Yes,
Now what happens?
Unique of
It will skip 2.
Two is
it's
discard.
already present.
Okay, we skip 3, 5, 2. Sorry, we skip 2. Now this will insert 3 just before unique of 5, 2. This will
And insert 5 just before unique of 2. And unique of 2 is 2.
unique of 2 is 2, right? And then you bring all of them together and you get 1, 3, 5. Okay, so that's one way of writing unique.
Sir, I didn't get the last step where the element 1, the list that is having element 1, we are adding the first of L before the unit of rest of L.
Correct.
And but we are inserting here, no, between 1 and unique of 5 2.
Yeah. So 1 plus 3 is 1 comma 3, right? And then so sorry, which part did you
Sir, we are having the output is return first of L, and here first of L is 3, but 1 is thrown away, no? Where is 1 come from?
So it's coming from this particular procedure call, right? So first of L plus unique of rest of L, you keep accumulating this from there.
Sir, but we have not written in this.
This is the second occurrence of 1. The first occurrence we have already discarded. This is the second occurrence of 1.
Right, correct. So this one is this the one you are talking about? Yes. This one.
In this cell, no. In the next step, when we have the one time, yeah. At this stage, we have the we are returning 1 plus unique of rest of L. Okay, and in the next step, we will return 2.
We'll discard.
Yeah, we in the next step, 3 plus unique of 5 2.
Correct.
But we are keeping 1. Why we are keeping 1 here?
Yeah, that's from the previous recursive call, right? See this.
Because it is recursive. Okay.
Yeah. So you have to. Yeah, this is the way of writing the recursive call, which is where I don't, bring in all the graphics, right? So which is suspended, which is not suspended. You're kind of keeping track of the whole thing in one statement.
Okay, sir. Okay.
Yellow, it's yellow.
So this is like, see, this is the original call. This is the first call, right? First ever call. And this is the second recursive call. Okay. And both have the same return values. Okay. They have the same return values. Now, what I'm keeping track of is the return value of the first recursive call. Do you get that?
Yes, sir. Yes, I got it.
Okay. So first recursive call, I'm keeping track of that output, that return value. And therefore I have to keep building up. So every time I call it, I can't throw away this part. I have to retain that and then keep adding to that.
Okay.
Okay. So now let's look at the other unique. The other unique is what? You retain the first occurrence. This is the answer that all of you gave first, right? 1532. Now, what is the strategy that you will follow here? So again, break the list into 2 parts, but how will you break the list into 2 parts?
Sir, we have to do it in the recursion method.
Yeah, same recursion, but how will you break the list?
First rest, last rest.
Last and
init, right?
Last and init.
Okay. So now again we ask the same set of questions. The questions do not change, but how you break the list alone changes. So is A in the init of L?
Yeah. Then we discard it.
Yeah. Then you discard A, right? So can you tell me the pseudocode for this?
If is member last of L init of L, then
Init of first of L should be discarded.
Okay, return what? Okay, in that case, return what?
Return unique of init.
Init of rest of L.
Okay.
Rest of init of L. Isn't it?
Unique of init of L.
Init of L.
Unique of init of
L.
Yeah.
L, yeah.
Unique of init of L. Yeah.
Right. So if A is present if last of L, A is present in init of L, A, B, C, B, right? It is, right? Then you return unique of init of L. You throw away last of L, you only return the unique of init of L. Now, on the other hand, if A is not present in the init of L, so what do? You
add it to the end of
return unique of init of L plus
last
unique of init of
plus
L
last
plus
of
plus
L.
A
Last of L.
plus last of L.
right? So here you can use the term append, right? This is
Append, yeah.
Here you are actually appending, because append means adding to the end, right? So Earlier, also you used where you are inserting you are inserting first of L, now you are appending last of L. So let's again very quickly write this down. So if it is a member, if last of L is a member of init of L, return this, else return unique of init of L plus plus last of L, same base case, right? Base case is same.
Yes.
Okay, now let's do this example. Now you want to find the unique of this. So
We will
last of
discard 2.
we'll discard 2, right? So we'll discard 2,
Discard 5.
discard 5.
3 also discard. 2 is already there, so we will init of this plus 2.
Yeah.
We'll init of L plus 2, and 1 we discard. 3 is not present there, so unique of 1 5 plus 3 plus 2.
2.
Similarly, unique of 1 plus 5 plus 3, and unique of 1 would be 1. So it will return 1 5 3 2.
Okay, that's correct. Right. So that's good. So we have written two procedures which essentially do the same thing but in slightly different ways. Okay, so depending on what you want, depending on what the specification is, you will have to do either one of these two. Okay, so the machine at the end of the day is very sensitive to these things, right? If you don't specify what you're doing, it will you may end up unconsciously doing something else, right? And you have to be careful. Okay, so I'll also do just two more examples. We'll wrap up by 8:30. Now, palindromes, right? So I hope you all know what palindromes are.
Yes.
Okay, so madam is a palindrome. Now, so what's the logic? If you want to find out if a given word is a palindrome or not, what do you look for?
The first of L and the last of L is this L.
Okay, so you look at the first and the last, and of course you look at the second and the last but one, and so on, right? So you do that. Now, this is for an odd number of letters, right? 5 letters are there. Now let's look at what happens if you have an even number of letters. Of course, you do the same thing, but what's the subtle difference between odd lettered words and even lettered words?
We will check that if the length is
case will vary.
2.
Okay, so at without going into the coding part, at a word level, right? So at a word level, what is the main difference?
One letter will remain in the end for odd.
Yeah, that one letter can be anything, right? So that's
There would be any least to come.
that could be any random letter, and it doesn't matter. It's not figuring into the matching part, right? So whereas in the even lettered words, all pairs matter in the sense that every letter will occur at least twice, right? It will have a pair. Whereas for odd lettered words, you will have one letter which is not having any pair. It's its own pair. Okay, it's an isolated word, a letter. Okay, so that's the catch. So another trick or another suggestion when you start writing code, okay, you must get used to start writing code because in a month's time you will be enrolled in Python, and you'll be doing this not just in Python but for the rest of this degree, right? You'll have to write several lines of code. One suggestion is always have some examples, especially if you're a beginner. If you want to write palindromes, right? If you want to write a code to detect palindromes, always put down an example to your right, okay, to wherever you're working. Just put down an example and use that example to write the code, okay? Of course, your example should be rich enough. For example, here I'm using 2, right? So if I use only odd lettered words, I may end up writing a wrong piece of code because I might miss out on the nuances of even lettered words, okay? So always have 2 or 3 examples to your right, and on your left, start writing the code. Okay, so we'll again follow the same procedure of filling in the recursive logic first and then going for the base case. So first, recursive logic. What's the first line of code?
If first of L is equal to the last of L, then we will return the init of rest of L or rest of init of
L.
Okay, almost there. So you are saying you will return init of rest of L. Will you return init of rest of L or will you return something else?
Hmm.
You can just return true also. Okay, so the first part of what you said is, so you're there, you're almost right. Just one small tweak you have to do. So if first of L is equal to last of L, then you return something. You are saying you will return init of rest of L. Is that what you have to return?
We have to call the procedure again to check.
Exactly. That's the only point you are missing. That's all, nothing else.
Yeah.
So if first of word is okay, I wrote it the other way, but anyway, it's the same thing. So if the first of word is not the last of word,
Return false.
it's you know right away, right? So it can't be a palindrome. So you return false. Else, you return the palindrome function or on init of rest of word. Okay. So did everyone get this? How we are doing this?
Yes.
Okay.
Yes.
Okay. So now that's all. That is you have done. You are done with the recursive procedure. So you will just get rid of the first and last, and then you will keep calling the procedure on smaller and smaller words until
the length is greater than or equal to 1.
Okay. So what should be the base case? If
if length is
length
less than equal to 1.
Length of L is less than equal to 1.
Good point.
So
So
greater than equal.
Then it is true. Return.
if length of word is less than or greater than, what should I write?
Greater than equal to 1.
Okay. How many of you think it's greater than or equal to 1?
Or we can less than equal
Less
to
than
1
sir,
return
because
false.
yeah.
For base case
If it is greater than, then we have to
greater than, you have to then execute the
Okay. So you
Return true. Less than equal to 1 return true.
return
Okay.
true. Yes, sir.
Okay, here is a question. Now, why is this less than or equal to? Why not double equal to 1? What will happen if I use double equal to 1?
For sir, even number of letters,
even number.
we cannot have this condition
Correct, right? So for the even lettered words, you will end up
with the zero.
Zero. Empty list. We will
Zero number of
with an
elements in the
empty
list.
correct, right? So you'll end up with an empty list and you will have to, that won't be caught by the base case, right? So you have to have less than or equal to 1. Now, let's very quickly go and see how it works. So if I call Pally on Madam, list of characters, right? This is a list of characters. What will be the next, what will be the output of this?
Value of ADA.
Value of ADA.
And then value of D. And it will return true.
This will be true, right? So now let's do noon.
Value of OO. And it will empty list, value of empty list, and it will return true.
Okay, and now it's not correct if we don't do something which is not a palindrome.
Value of UL, and it will return false.
Right?
It is not equal, so it will be false.
Yeah. Okay, so that will kick in and it's false. Okay, one final example of recursion.
So can you repeat the last line? How return Pally init rest word? Can you explain this line, please?
Yeah, sure. So let's let me go to this particular screen. You have, this is the last line, right? So you want to know what is Pally of init of the rest of L. Okay, what this means. So let's take a concrete example of M. So let's say A, B, C, A, B, B, A, right? So let's take this. Assume that L is this. So whenever you see an expression like this, okay, which is very complicated, this is what? This is this we call as a composition of procedures, right? Or functions. One function inside the other. So the easiest way to understand is this is take the inmost, take the one which is right at the heart of the composition, right? Rest of L. Now, what is rest of rest of L, this is
BBA.
rest of this, right? So rest of, what is rest of this?
BBA.
Right? So this is BBA. Now this is BBA. Now this is rest of L. So you are done with the innermost part, right? Always when you have a composition of procedures, the rule is you should go inside out. You should start with the innermost expression, innermost procedure, and then gradually work your way out. So your rest of L is done. So init of rest of L, right? So next, that is what you have to do. Now init of rest of L is what?
BBA is BB.
Init of rest of L is this thing, right? Init of BBA and init
BB.
is BB, right? So you are done with the second, right? Inside out, you are done with second. Now you have to do the final one. So pally of init of rest of L is what you are going to ask. Is this a palindrome? Is this a palindrome or not?
Yes.
It's true, right? Of course, you have to do one more step. Because basically, you have to call it again on this and recursively you have to do. But this is what this step amounts to. So what is this step doing? It's basically cutting off the first and last letters, right? You want to find a way to, this is what you're doing, right? So you want to find a way to remove the first and last letters from your word. And how do you do that? You take rest of L. Rest of L will remove the first word or the last word. So for first letter or the last letter?
Last.
It will remove the first letter, right?
First of letter. First.
Rest of L, right? Rest of L is what? Everything other than the first letter. So this removes the last letter.
Yes.
Init of rest of L will do what?
Last of
Remove
the
the last letter.
Removes the last letter, right? So together, init of rest of L will remove the first two letters. And once you remove that, you can continue calling palindrome from on this particular shortened word. Okay.
Okay, sir. Got it. Thank you.
Here is one question for all of you. Now, if the length of the word is n or n, yeah, if the length of the word is n, so if it has n characters, how many times will I call pally, right? What, or rather, okay, yeah, how many times will I call pally? What is the maximum number of times that I'll have to call the procedure if before determining if it's a palindrome or not?
N by 2.
n plus 1. N by 2 plus 1.
2.
N plus 2,
N by 2 plus 1.
Okay, let's look at that answer. N by 2 plus 1, right? Or n by 2, right? I'll take both these answers and we'll see which of these actually works.
We have to, there will be two, I guess, one for odd and one for even.
Good point. Okay, so let's take the even case first. Okay, assume that it's even. So
For that case, it would be n by 2.
Okay, for even, what is it?
For
N by
even, it
2.
would be n by 2
N by
plus
2.
1.
Okay, can you tell me how the n by 2 comes and how the plus 1 comes?
N by 2
Sir,
is
for both the cases, even and odd, it will be equal, whether n by 2 and n by 2 plus 1,
no.
I think.
N is an integer, so it's
No,
okay. Anyway, for the even,
it should, for odd, it should be n1 n plus 1 divided by 2.
okay, now let's do the even first, right? Even first. Now,
Okay.
can you tell me which of these two is correct?
N by 2 plus 1.
Okay, please, can you please explain?
If we have moon, so it will call for 4, there are 4 letters, so 4 by 2 plus 1 times for the empty list as well.
Okay, so there are, let's say you are saying you start with 4-letter word and you are calling it on, you will first call it on the 4-letter word, you will then call it on the 2-lettered word, and then you will call it on the empty list.
Empty list.
Is that correct? Is that the logic?
Yes, sir. N by 2 plus 1 for even.
Okay, so let's go with n by 2 plus 1.
Sir, for odd, sir, it is n minus 1 by 2, and for even, it is n by 2.
Okay, odd is what?
N minus 1 by 2.
Okay. n minus 1 by 2 you are saying. Okay, now,
For me, it should be n plus 1 by
N
2.
plus 1 by 2.
okay, I'll write down both and then we'll figure out which one is correct. N plus 1 by 2. Okay. So,
For 5, if I have madam, I will call palindrome for M first, then A, and then for D.
We are not calling Palindrome for D, sir. No.
We will be calling for that. It will just return true for that.
First,
But we will call for
only
it.
one single element it will return true.
okay, if we are calling it on 5-letter word, on the 3-lettered word, on the 1-lettered word also we'll call it, right?
Yes, sir. So
Okay,
it should be n plus 1 by 2.
so this is 5 plus 1 by 2. Okay, okay, that's correct. So n plus 1 by 2. Now here is a follow-up question. Now, can I club these two formulas into one single formula? Is there a way to do that? So this is what? I mean, I also don't know the answer. I'm just asking you.
N plus 2 by 2. This is n plus 2 by 2. This is n plus 1 by 2.
Or maybe this is, let's retain that as n plus n by 2 plus 1. And this is what? This is n by 2.
N by 2 plus 1 by 2.
Okay. So now both are having n by 2. So let me know this. Okay. This is what?
We can do like if n by 2 is double equal, if it is like a divisible number, then we have to add or something like that.
Okay. So do you all remember the floor ceiling function?
Yes, sir.
Can we do something like this? Will this work? Just I'm just thinking.
Sir, it can work.
Okay, what will n plus 1 by 2 floor of this be? If n is even, if n is odd, what will happen? If n is odd, what is this? So if n is odd, what is floor of n plus 1 by 2?
Even.
So n plus 1 is even. It's actually just n plus 1 by 2, right?
Yeah.
If n is even, what is floor of n plus 1 by 2?
Or it would be odd. It would be a fraction.
See, floor of n plus 1 by 2 is always an integer, right?
N by 2.
N.
Even.
Just try it out for n equal to 8. For n equal to 8, what is this? What does this give?
So it would give 4.5.
4.
Yeah, for that it would give 4.
For that, it will give 4. Okay, now, what do we need? We actually need 5. Correct? So, can I replace this as the ceiling and will that work?
Yes, sir. For ceiling it would work because it would take the next value, next closest value.
Okay, let's try this. So, I make this the ceiling. Now, if n is odd, n plus 1 by 2. If n is even, will this be n by 2 plus 1? Is that correct?
Yes, sir.
Yeah. It is working for even.
Yes, sir. That would work.
Okay, I think is this correct, right? Okay, so maybe I'll have to revisit this, but anyway, you can please work it out. This is just a math exercise, okay, nothing serious. But anyway, let's move on to like the final example before closing.
Yeah, and before even we proceed, like I have one question on this recursion.
Yeah.
So can you discuss that as well at the end?
What is it?
From one previous year question. So.
Okay, yeah, let's try. Yeah, sure, we can do that. I'll just finish off this the last part, which is am I sharing the slides now?
Sir, I have a doubt. When we are having only one element in the list for the palindrome, how we are calling the palindrome there? We are just putting returning true.
So if there is only one element, we are just returning. Yeah, we are not recursive. There's no recursive call there. We just it's the base case, right? So we return true there.
Yes, sir. So that's why I told that it will n by 2 for the even number of elements in the word. N by 2 times we will call the palindrome.
See, there are 6 letters, right? 6 you call, 4 you call, 2 you call. So you already called it 3 times.
3 times. Yeah.
You will call it one more time, right? When it becomes empty list. So you'll also call it 4 times you will call, right? Totally. N by 2.
For the empty list, sir, for the empty list, we are returning truth. Then whether
But
we are
you'll have
call,
to call the procedure for that to happen.
Yeah, you will end up calling, right? You have to call. So
okay, sir. Okay.
Yeah.
Got it.
Okay, so this is more of a math example as it's given in the assignment. It's like there's a nice trick to find the HCF of A comma B. So if you have two numbers A and B, you all know HCF, right? So if both A and B, if the HCF is D, right? Then the HCF of B and A minus B is also D. Okay, so that's the basic idea behind this HCF problem in practice assignment. So I just work it out here. So do you all agree with this particular line here? Is this clear, or are you haven't seen this before? Anyone?
So mathematically that is true.
Okay, yeah, that's what I'm asking. That's clear to you all, right?
Yes, sir.
Okay, so let's just quickly do this for a particular example of 18,8, right? So you do 18,8. Now the basic idea is this, right? You take up two numbers and then you find out the HCF of the smaller of the two, right? Smaller of the two is what? 8, and the difference between the two. Okay, so you have 18,8, two numbers, and then you have transformed that problem into a smaller problem where you are finding the HCF of 10 and 8. Okay, and both are the same. You are using this formula. Just treat this as a formula, nothing else. So you keep repeating this procedure. So 10 minus 8 is 2, and then you take the smaller of 10 and 8, which is 8, and you keep doing this until you hit the HCF, right? This is one way to compute the HCF. So we are going to do this recursively. Do you all see why this is recursive? HCF of original pair of numbers is equal to HCF of some other pair of numbers, right? So that's how the recursion comes, right? Self-referencing, that's recursion. So can someone tell me what will be the recursive statement here?
Sir, the first line SCF of 18,8 is SCF of 8,10 or 10,8?
Both are the same, right? 8, 10, 10, 8, both are the same.
Yeah, it is mathematically same. Okay.
Okay, but yeah, that's a good point. We'll come to that. So what will be the recursive statement here? Think about it as a formula, right? HCF of A comma B is HCF of B comma A minus B. For now, that's all you need to know.
You can use the same thing as we prepared, right?
Return.
You have to start with if A greater than B. Okay, return what? You have to return what?
The same.
I mean, return HCF of A comma B itself, or
A comma.
So B comma A minus B. You got to return.
Okay, right? Right, so that's the same, right? Return HCF of A minus B comma B. This is what you have to do. Now, that's the simple part. Now, the slightly trickier part is figuring out the base case and all these things here, right? Here, the recursive call is very simple. So, what will be the base case?
A is equal to B. If A is equal to B.
Correct, right? That's correct. If A is double equal to B, that is. So, what will you return there? A or B? A or B, both are the same, right? Now, here is a slight change that I'm doing. So, notice that when you have two numbers, I'm always making the first number bigger than the second number. Yeah. Okay, so if A is smaller than B, then I return HCF of B comma A. So that always the first number is bigger than the second number, and then I plug in the base case.
Yeah, fine.
Okay, so that's all there is to the HCF. Now, yeah, officially, which is what I prepared. Now, any questions? See, no activity questions, please, because that you can ask Deepak sir in the next session. Now, anything other than activity questions, maybe I can take now.
Sir, adjacency matrix for the coding part, it is left.
Adjacency matrix we saw, right? Is there anything specific that you want to know in the adjacency matrix? We computed the adjacency matrix for a few graphs, right?
Yes, sir, we did it, but how to write pseudocode like ij for each for loop? I didn't understand for the same.
For loop.
For loop part of that procedure.
Sir, actually, the thing is sometimes we are running the for loop thrice. Let's say I mean for each I in rows, let's say some dictionary, and then we are again running for each j in columns. Let's say again we are running the for each for the rows. Let's say k in rows. So how does that work actually? I mean that's my problem. I don't know if he's
Yeah, the same
issue,
problem, sir. I am facing with.
Yeah, so that's the thing.
So you want to a triple nested loop, is it?
Yeah, yes. I mean, first is rows, then columns, then again rows. So in such case, how can we? I mean, how the rows and columns we gotta check?
Okay, let me write down what you are saying. So for each I in columns of.
So rows. First is rows, or yes, sir, anything would work. I mean, columns, rows, columns, or rows, columns, rows. Anything would work.
Okay, so rows of rows of graph for each j in columns of graph for each k in rows of, let's say, graph again. Now, what are we doing inside this? I mean, I need a concrete. So from I'm not sure from where this particular. What is the context surrounding this question? So I'm a bit lost. So what do we do inside the loop? Do you have any idea?
Maybe we can graph. We can graph I k 1.
Okay, so one hop neighbors you're saying.
Yeah,
right?
one hop.
Okay. Okay, that's good. That's a good idea. So let me put it here. So find all nodes that are reachable from okay, so let's look at this as stations, right? We can look at this as stations that have exactly one stop between them, right? So we pull this graph here. Okay, so you have a four. Okay, so this is not a DFS question, by the way. This is just a okay. Now, what are we asking? We are asking the following, or maybe let me not complicate it with stations and all this, right? Find all nodes that okay, I'm just wording it. My wording it is kind of bad, but so let's say we have this problem. Find all nodes, all pairs of nodes that are Okay, does that make sense?
Yes,
Find
sir.
all pairs of nodes that are separated by exactly one neighbor. So, for example, 1 and 3 is going to be a pair, right? So 1 and 3 is
0
separated.
and 2 and 3 and 4.
Okay, so let's do this in this case for each I in rows of graph and for each j in columns of graph. Do we need a triple nesting for this?
Sir, can you tell the example from the assignment part or somewhere?
Assignment part right now, I may not be in a position to tell this, but
It is from the week 10, I think.
let's do it this way, right? If graph of ij equal to 1, if there is a link from I to j, let's call this I, this is j, and this is k, right? So if there is an edge from I to k and there is an edge from k to j, okay, what can I say? Is that so? There is a I to k, so let's call this I. If this is a bit confusing, let's call this I. This is node I, this is node j, and I want to know if there is a node k that is connecting both, right? So if graph of ik double equal to 1 and graph of kj double equal to 1, then I'm just counting, right? I'm just counting. Okay, so is this a kind of situation that there is some difficulty in understanding what is happening here? Am I right in thinking that this is causing some difficulty? Or is this part clear to all of you?
So I think this part is clear, but maybe we can take an example from some assignment where we need this triple for each loop.
Okay.
Where matrix is involved, perhaps that might help clear a lot of doubts.
No, in this example itself, you can just draw a graph and explain.
Yeah, I know.
Okay, so you want to know how the you want to know how this graph, the execution of this graph, or with the matrix involved. Is that correct?
Yeah, with the matrix case. Yeah, that's the question they have asked.
Okay. Let me pull this up here so that the whole thing is in the same place, right? So this is the graph. Okay, this is the graph. And that is the code. And let me also draw the matrix corresponding to this. Okay. Sorry, I'm just going back and forth, but yeah, let's draw the matrix. The matrix is going to look as follows, right? So 0,
1, 2.
0 to 0 is 0, 1 is
1,
2 is
0, 3 would be 1, and 4 would be 0.
Okay, this is T. This is 1.
Then we copy this 1.
For
1, 0, it would be 1. 1, 1 would be 0. 1, 2 would be 0. 1, 3 would be 0. And 1, 4 would be 0.
Okay.
For 2, it would be 2, 0 would be 0. 2, 1 would be 0. 2, 3 would be 1. 2, 4 would be 1.
Okay.
3, 0 would be 1. 3, 1 would be 0. 3, 2 would be 1. 3, 3 would be 0. 3, 4 would be 0.
Right. Finally,
4 for 4, 0 would be 0. 1 would be 0. 2 would be 0. 3 would be 0. So 2 would be 1.
2 would be 1, 3 would be 0, 4 would be 0.
Okay, 4 would be 0, right? So this is the graph,
Agency in the matrix for this graph.
right? So let's call this. Oops, I don't want to change orientation. No, let's call this graph, right? By the way, this now. What happens when we? So how do we loop through this? Is that the question? How do we loop through this graph?
Yes, sir.
Okay, so for each I in rows of graph, right? So now perhaps it will help us if we replace the rows of graph with what it actually means. So what is rows of graph? What is it going to return?
It would be key. So for this matrix, it would be keys of graph.
Oh, okay, so it will be the. So this is the actual syntax is keys of graph, is it? Or it the keys of graph, right?
For
So,
each I in keys of graph.
Okay, so what are the keys of graph here?
0, 1, 2, 3, 4. In any random order, it can be.
Okay, assume that it's in the proper ordering, right? So whenever you are looking at a nested or triple nested code like this, and you are seeing rows of graph, columns of graph, if it's always convenient to replace it with the actual output of that operation, right? So that will at least demystify level of it.
Then it will call for columns I, graph I. For keys of graph I.
Okay, okay.
Keys of graph of I.
Got it. You are right. So keys of graph of I. Okay.
Then it will check for J.
But it can be the columns, right? I mean, what I'm doing is I am going through every pair. It's not efficient. I get that, but I'm just looking at every pair of nodes in the graph, seeing if there is an edge between I to K and K to J.
Correct.
Right. So let me replace this with 0, 1, 2, 3, 4. Okay, see, this is what is happening at the end of the day, right? So rows of graph, columns of graph, whatever it is, you just replace them with the actual values. Now, so
but
I don't.
For the third for each loop, sir, what will we write? So for the first loop, we wrote that for each I in keys of a graph, and for the second, for each I, we wrote for each J in keys of graph I. Then to check for K in, what will we write for this one? It would be keys of
So it could be either rows or column, right? If you're looking at
keys of J.
No, there is no key for J, right? That is the problem. It's not a nested dictionary inside a nested dictionary.
Yes, sir. What is the innermost?
Right. So see, as I said, my pseudocode is a bit rusty, so I am.
We will not need it or will we?
So the rows of graph is what? In CT do we have rows of? Is there a row function that is defined?
So for a matrix in a code form, if we talk about matrix in code form, we have a function rows. Rows is sort keys of matrix.
Okay.
So that is rows. So it will return me the sorted list of keys of that particular matrix. Rows will be that, and column will return. Column would be sort keys of key of that particular row. So it will return
like in this, like it will return 0, 1, 2, 3, 4. And for particular 0, if it is column, it will return for the 0,
1, 2, 3, 4. 0, 1, 2, 3, 4 for that also.
The person who has asked this question, it would be better if they share the question. Actually.
Yeah, exactly. Because for the third, for each loop, I'm unable to.
Okay.
Why this third? I didn't understand. Like why this for each key the third.
Yeah, we don't really need, I think, for that.
Actually, they have some other doubt, I guess.
Yeah.
Yeah.
Maybe we can actually take a question that actually have for 3 for each loops and that.
Yeah,
That
yeah.
might help. Yeah.
It's better, yeah. So anyway, this is wrong. Whatever I have written here is wrong, by the way, because we'll be double counting.
The third for
Correct.
each K is not even needed, I guess.
Yeah, yeah. So anyway, so if anyone is watching this later on, please note that this is not the answer for whatever question I have written down here.
Also, sir, in this case, it will be double counting because we have, it's not a directed edge.
Correct. Yeah, you're right. So ij, ji, all this will be double counted. Anyway, yeah. So that is a better method. If you can tell me what.
If Sharon is there, if you could refer to that question.
Yeah,
There were questions in, I think, previous week. Let me just try to find if there are some.
Okay.
And if you're finding in the meanwhile, sir, if you could explain, I have shared the link.
Where is it? In
the chat. In the chat, I have shared the link. In that question number 25, it is related to recursive procedure.
Okay, so let me, question number 25, is it?
Yes.
Okay, let me download this. Okay, question number 25. So where is CT?
Just below the statistics.
Computational. Okay, what is the subject name? Which is called CT or computational?
CD, sir.
Computation.
1 second. I am not able to. Can you tell me the page number?
Question number 25. Okay, I will refer.
Oh, it's the 25 in the whole thing, is it?
So the numbers are continuous.
Okay. 25. How many times will the procedure end fib, right?
Yes, sir, that question.
Okay, let me just copy that here. Consider the following pseudo code. Okay.
So there's one particular question in practice assignment of week 10 that uses this triple for each loop.
Is it? Oh, 1 second. Let me just quickly.
Sure. No issues.
Okay, so consider the following pseudocode. If n is less than 1, return n. If not, return n fib of n minus 1, there's n fib of n minus 2. Okay, how many times will n fib be called if n equal to 5, excluding the main call? Okay, so what is the question here exactly? You want to, is there any?
How many times this procedure will be called?
Okay. Right. So for this, it's easy if you can draw the what we call the recursion tree, right? So there is a recursion. There's a tree. There's a way of representing it as a tree. Okay, the recursive calls. So I'll just do that here. Let's look at Fibo nfib. It's called, right? So nfib is called on 5, right? So
yes,
nfib. Maybe it's better if I use rectangles. Okay, so nfib is called on 5. So nfib there'll be two branches emanating from this. One is nfib of 4 and another is nfib of 3. Is that correct?
Yes.
So you have these two. This is called a recursion tree, right? So we are building the tree here. Now this will do what? Nfib of 4 will in turn call nfib of 3 and nfib of 2. So you will end up having 2 more calls. Now, what is the base case? Nfib n less than 1, right? So this will nfib of 3 is going to call when we are doing a DFS, right? If people realize what we are doing is a DFS kind of thing here, right? So 3 and 1. So that will be this. Now this will once again branch out into
1 and 0.
1 and 0, right?
Yeah, 1 and 0.
1 and 0, and both are going to terminate, right? Because the base case will come in and this will terminate. So this is going to end up with this. Now nfib of 1 is again going to terminate. So there's nothing below this. Nfib of 2 is going to have something similar. So you will have this again, both of them will terminate, and nfib of 3 will have this kind of a structure, right? So
Same, yeah.
because I'm very easily drawing it here because I have the tools. In the exam, you'll have to do it. So, but it's not hard to draw this recursion tree, right? So now if you count, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I don't know what's the answer actually.
It's actually 24, sir.
Wow, interesting. How did it become 24? How can it be 24? Because this is recursion.
Show the pseudocode again.
Okay, let's start from the first, right? You are passing 5, so 10 less than 1 anyway, that's not the base case. So you'll return nfib of
4 plus nfib of 3.
Right, so each one will be a call, right? So each one will have to execute. So you'll do the nfib of 4 first because you are going to read it from left to right. So nfib of 4, that will in turn call 3, 2, 2, 1, n less than 1, right? Oh, n
So
equals.
it will for call for nfib of 1 also.
Correct, you are right. We forgot. So nfib of 1 will go down into
0 and -1.
So that's the catch. Sorry, we missed that. So
0 and -1, and then for each nfib of 1 we will be doing this one.
Right. Each nfib of 1 we'll have to do that. So
there is another one for nfib of 3 in between the.
Wow, super complicated.
It's going to be complicated. So.
Yeah, but anyway, at least for completeness sake, let us throw in the. Okay.
Then we will have to do it for 2 more nfib of 1.
Where are they? They are here.
And 1 on top of that.
Cool. It's nice to look at, but messy. Yeah, I'm hoping it will come out to be 24. So no, it's
too complicated.
Yeah, are you asking, is there a mathematical formula kind of thing that you can? Is that your question?
That's what I was asking, because such question in the end term, it would cost us time, so much time.
So 1, 2, 3, 4, 5.
Okay, so see, what is it doing? It's actually computing the nth.
So it's calculating the Fibonacci series.
Right, so I think so 24 is what? Is it in any way directly related to?
So the Fibonacci of 5 would be, I guess, 120. So in terms of like, it is returning n. So something like adding two numbers and multiplying something, we should get 120.
Right. So how can you solve this? I'm thinking if there is a way to solve this without using the recursion tree, right? So without constructing the recursion tree. See, one thing that you could do is once you identify the number of calls required for Fibonacci of 3, right? So this you can do. You can get rid of all this without actually having to build the recursion tree. Let's do the following, right? So
now we can identify for 3, and wherever 3 is there, we can add the number of calls.
exactly. Yeah. So So let's just expand this part alone, right? So 3 n fib of 2 requires how many calls? 1,
1, 2, 3, 3 calls. 2, 5.
5 calls, right?
5 calls.
Like 4 and 4, including 2, yeah. 4.
Including 2, it will be 5.
5.
N fib of 1 would require 3 calls.
Yeah,
So,
so 5 plus 3, 8, right? So
9.
Including 3, 9, right?
9. Yeah.
So there is 9, there is let us write down 9 here. So there is a 9 for this, including fib of 3 and n fib of 3. There is a 9 here, including n fib of 3. So that's 18 plus 19. So what are we missing?
So we deleted n fib of 2. So for n fib of 2 will also be there. So it will be what? 1 to 5. 5 for that. So it would be 5 plus 9 plus 1.
Sorry,
So,
did you get that?
Under NP4 we
And
Complete again.
4 we missed one, like 4 would be 3
4.
and then
3 and it would be 2, right, sir?
2.
N fib of 2.
Oh, sorry, right.
So
Yeah.
it would be n 9 plus 5, 14 plus 1, 15 for n fib of 4.
Sorry, I missed this, right? Yeah, so this will be assuming that whatever branching is there. So n fib 2 is how much?
It's 5. So
5 including 2, yeah.
including 2, it will be 5.
Okay, so this is 9 plus 5.
So it will be including 4. We can see that it's going to be 15.
23 now. This will be 15. Okay, this will be 15. Okay, and n fib of 3 will have 9, right? So 15 plus 24. Yeah, correct. Yeah, so that's I think this is a better approach, right? So where you have to expand the recursion tree up to a certain point and then reuse the values for
Number
other.
of calls.
Yeah.
Okay, thank you, sir.
Okay, so shall we stop now? Is that fine?
So there we were solving those nested for each loop. So for that there are 3 questions in a practice assignment of 10 and graded assignment of 10. In graded assignment 10, there are 2 questions, 6 and 9. And in practice assignment 10, there is 6. We can look at any of those 3 questions for that.
Okay, practice assignment. Let us look at practice. Maybe with that I will close, right? So practice assignment what?
Practice assignment 10, question number 6. It requires 3 for each.
Okay, practice assignment 10, question number 6. I hope it's not from complete the code business. Is that complete the code? Oh,
Yes, it is.
super. Okay. Okay, so
yeah, it's a complete code.
Yeah, big codes. It is not even fitting into my. Yeah, one more hop, right? So what is this question about? Assume that there are n stations. It's a big question. This is the question. I copied it and this is what came out. But anyway, so we have n stations. Stations are the nodes. There's a direct train. Okay, the graph. Station J, we can find a one. Okay, so we have to find what are we asked to find? We have to find B and B of ij is 1 if there is a direct train. We are given a matrix A. Okay, A is where is the matrix A?
I think it's
Oh, that's direct.
Recursive,
Matrix is direct, right? So let's condense this question. Direct is a matrix. Direct is one if there is an edge from I to J.
Yeah, there is direct train from between those stations.
Okay, that's the only important information in all this text, right? So if there is a and zero otherwise, right? So this point number one, and what else they are saying? And find a non train. Okay, so is J reachable from I or not? So B of ij is one if B of
It is
one
it
if
is reachable.
okay, and you need to use you need to use the direct matrix to find this. Okay, so what are we doing? Keys of direct n, so n stations, you are creating a empty matrix, right? I hope you all know all this. You are creating
Yes,
and then you are
each
looking
value would be 0.
Right. So for each row, for each column,
Indirect.
so
We will reference that dictionary for the direct for this.
right. So if there is a direct train from R to C, then C is reachable from R, right? So B of RC is direct of RC, right? It will be
it will be 1. It will be 1.
Okay, so this is also clear. Now here, how many hops we can take? So hops less than n minus 1. Can we reach from I to J in one hop, right? So currently, we are going to do one more.
We will call procedure one more hop for this one.
Okay, so this one more hop is what we have to fill in, and we have to fill this in with what is the correct answer. Let us not worry about wrong answers. Let us quickly go and copy the correct. So, what is the correct answer? Is it A, B, C, D? Can you someone tell me?
Let me see. Sir.
A is the
For
correct.
this, A. No, A, not A. There are 3 correct options for this one.
A, B, and C.
A, B, and C. A, B, and C are the correct options for this question. So 3 correct options.
I am sorry, I got disconnected. See, I'm unfortunately not able to share my screen now, so it's kind of a bit late. So shall we do the following? Is it okay if I can write down something and share it with all of you for this particular problem?
Yes.
Will that work? So do you all access discourse regularly?
Well,
Yes, sir.
I'm not able
Yes,
to
sir.
access Discord.
Yes, sir.
But
Okay.
half of them, I guess, don't have the student mail ID too.
No, I do have student mail ID, but there's some issue with my student mail ID. I've written to a support team as well, 11 or 12 times, but we are not able to. So there are some students who cannot access this course with despite having official email IDs.
Okay. 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 So that might be a problem, or I can do one thing. I'll share it with Deepak sir, and then
Sure, sir. Sure.
yeah, that will work. Okay. So yeah, that's all I had. So
So before we leave,
yeah.
I would like to request you a thing. Like, if you could please take a session for the week 9 and 10, because like due to the quiz and all other things, like there we didn't have a proper session.
Open
for
session
these.
for that. Yeah.
So it would be like, I would request you please, if you take the session, if you have time.
For 9 and 10, is it?
So the matrix and adjacency matrix those are a bit confusing at times.
Okay.
Maybe the problem really not isn't the adjacency matrix. Sometimes the transversing through those matrices that creates the problem.
Like where to like
Correct.
how
Correct.
to get the adjacency matrix and how to apply the code.
Yeah.
Because from mathematics point of view, we know exactly what to do with adjacency matrix, how to build it, how to
Yeah.
check for the spanning tree, MCST, everything. That is not a problem. From a coding point of view, it gets really hard sometimes.
Especially it's a nested loop, especially if it's a
especially
nested
nested
loop.
loops. Yeah.
Like from week 1 to 8, I didn't have that much problem, but like these 2 weeks, I'm having problem, and we didn't even have a proper session for that.
Okay. Okay. So sure, we can have one, but I need to know. So what will work? Like will taking up these practice assignment questions or graded assignment questions and solving them, will that help? Or
Yes, sir. I think that would work.
Sir, I mean, I have a suggestion on this. I mean, the way you took today's session, I mean, you took some visualizing things, and then you took the examples. So if you can conduct that in such a way, that is really helpful, because today's session was fantastic.
Okay. Okay. So clubbing the, say, questions with this kind of
that would work.
Let's decide on some outstanding questions, and then based on that, whichever concepts will come up, we'll seek an explanation on those concepts only.
So in the graded assignment of week 10, there are 2 questions related to this, transversing through nested for each loop, question number 6 and 9.
Okay.
And in the practice assignment, we were discussing that question number 6. So I think maybe discussing those questions might help.
Okay, sure.
Or so you can
right.
do like
so I can do that.
So otherwise you can pick the questions as of you took today, like you picked today, and you can explain them. So that would be better. Like that would be better.
Okay, so it won't be anytime soon. Anytime soon in the sense like not in the next 2 or 3 days, because see, I'm revisiting CT after like 3 years, right? So if I'm not mistaken, that particular one hop question, right, is something that was framed 3 years back, right? So I'm totally out of touch with the pseudocode. So if it's Python code, it's a different thing, right? You can always execute things, but pseudocode is like the specifics that I need to catch up with. So I can only do this sometime next week, let's say Monday, Tuesday types.
That is totally fine.
Yes.
Yeah, so we would wait for your session, and we can find the question if we have doubt, and so we can just ask you.
Okay.
Yeah, that would be better.
So we would wait for your session. Yes.
Okay, sure. Yeah, I'll do one more, but I need to prepare for that particular session.
Sure, sir.
Yeah, take your time, no issues.
Yeah.
All right. Yeah. So that's all I had. So Thanks a lot for joining. We'll meet again.
Thank you, sir. Have a good night.
Thank you so
Thank you,
much
sir.
for today's session.
Thank you, sir.
Thank you, sir.
Thank you.